Hello, everyone. Welcome to the last National Stock Assessment Seminar of the year. My name is Bailey. I coordinate this monthly seminar series that highlights interesting advances and topics in stock assessment science. We are excited to have Dr. Chengxue with us today. Chengxue is a research scientist from Stony Brook University in support of NOAA Northeast Fisheries Science Center. His research interests center on understanding population and ecosystem responses to environmental change and human perturbations. His current focus is advancing state-based stock assessment methods and developing spatial management strategy evaluation framework for fisheries management. And in today's seminar, he will present a fully generalized, spatially explicit management strategy evaluation toolbox. Without further ado, I'll turn it over to Chengxue. Thanks again for joining us.
Thanks, Bye, for the introduction. Let me share my screen first. Hi, everyone. My name is Chen, and I'm a research scientist at Stony Brook University. The work I'm presenting today was completed during my postdoc at the NOAA Northeast Fisheries Science Center, and this project is truly a collaborative effort. And I want to thank all of my co-authors here across different NOAA centers, and a special thank you to John Doroba, my supervisor, for his endless support and mentorship. It has been always a privilege to work with all of these talented fishery scientists. I really feel like I'm standing on the shoulders of giants. All right, today I will be introducing a new management strategy evaluation, or MSE Toolbox, developed to address spatial challenges in fisheries management. This toolbox is built on a state-based assessment framework, which allows us to leverage modern state-based features that greatly enhance its functionality, flexibility, and potential applications across U.S. fisheries and beyond. Here is a quick overview of what I will cover today. I will start with a kind of brief introduction to management strategy evaluation and Woods Hole assessment model, or WAM. And then I will walk through the SPASAM-MSE toolbox, especially its framework, the key features, and some of the ongoing work that's happening around it. And finally, I will walk through two applications and highlight some key conclusions, particularly drawn from the second application. I want to start by asking a fairly straightforward question. Why do we need spatial considerations in fisheries stock assessment and management? It's actually not a difficult question to answer. At a global scale, climate change is shifting where fish live and how they move, and it is also altering their biology and ecology. As a result, we're seeing increasing biocomplexity and spatial heterogeneity in fish distributions and population demographics. All of these kind of challenges one of the fundamental assumptions of many traditional stock assessment models. That assumption is panmixia, where we treat a stock as a single, uniform, closed population. But in reality, we know many stocks are spatially structured, move across regions, and respond differently to environmental change depending on where they are. So when spatial structure and movement dynamics are present but ignored in stock assessment models, population estimates can be biased and management objectives may fail. However, incorporating spatial structure and movement dynamics into stock assessments is difficult due to a variety of reasons, for example, jurisdictional constraints, limited data, and insufficient tagging or connectivity information. Now, let's look at the figure on the right. Let's assume that in reality, fish can move between regions, just like the diagram showing in the top left. In an ideal situation, we would like to be in scenario 3, shown in the bottom left, where we can use a spatially explicit assessment model. In that case, movement rates can be estimated directly from tagging data, and we have sufficient geopartitioned information to describe spatial heterogeneity in population biology and fishing pressure. But in practice, most assessments fall into scenario 2 or even scenario 1, where our ability to represent true spatial heterogeneity or population connectivity is very, very limited. So if this limitation is kind of unavoidable, then finding the best way to deal with ignored spatial structure becomes a central challenge for stock assessment scientists. In particular, we need to identify strategies that still allow us to achieve sustainable fisheries, not only at the global scale, but also within individual regions. To address these challenges and reduce their negative impacts, a management strategy evaluation, or MSE, is often recommended. This approach allows us to kind of test different management strategies and evaluate how missing spatial or movement processes influence both stock assessment outcomes and management performance. So, what's MSE? Management strategy evaluation is not a new concept. For many years, single stock, single region MSE has been promoted as a powerful tool for testing and comparing alternative management strategies. The basic framework is kind of straightforward, as shown in the figure on the left. MSE typically includes four key components. The operating model represents the true population and fishery dynamics. The observation model generates data, typically with observation error. The assessment model uses those data to estimate stock status, and the harvest control rule is then applied based on the assessment results, and the resulting catch advice will feed back into the operating model, update fishing mortality, and then the population dynamics as a response, as a feedback response. An MSE typically consists two phases, a historical period and a feedback period. The historical period reconstructs past population and fishery dynamics to ensure the system starts in a realistic state, and the feedback period simulates future management cycles in which data are collected, assessment are conducted, and the harvest control rule is repeatedly applied. By repeating this loop through the feedback period, we can evaluate how different management strategies perform over time and support better decision making. Because biological processes, data collections, implementation can all involve uncertainties. So MSE or MSEs are typically run across many realizations. These help us ensure that our results are robust, that and that each management procedure is evaluated fairly under a range of possible futures. Here, things become very challenging when spatial heterogeneity enter the MSE here, whether it's in population dynamics or fishing pressure or movement dynamics. In those situations, a traditional single stock, single region MSE is often not really adequate. When spatial structure is included in the operating model to drive population dynamics, we can expect the observation model, the assessment model, and the harvest control rule may all need to kind of incorporate some level of spatial considerations or flexibilities as well. This is why we need a spatial MSE platform that can handle these real-world complexities in fisheries management. When the SPASAM team discussed what should form the foundation of our spatial MSE platform, we were quickly drawn to the most recent stock assessment model developed at NOAA NOSI Fisheries Science Center. The model is WAM, which is a Woods Hole Assessment Model. WAM is a state-space age-structure stock assessment model. The state-space model is often considered as the next generation of stock assessment model because it can separate process error from observation error. And this separation allows us to more accurately capture the true underlying population dynamics. WAM is also fairly flexible. It can model many population and fishery processes as random effects, and it can link external environmental covariates as drivers of population dynamics. This gives us the ability to test whether environmental change contributes to population variation and whether incorporating those environmental covariates really improves model performance. So WAM has already been used in many age-based stock assessments in the US Northeast region, which makes it as a strong and practical foundation for building our spatial MSE platform. Now I want to highlight some recent developments in WAM. particularly those that allow us to incorporate spatial structure and movement into assessment models. WAM has now been extended to support multiple stocks and multiple regions with movement among regions and seasonal variations in movement processes. This is a major step forward for modeling spatially structured populations. Movement rates can also include time varying and age varying random effects, and they can be linked to some specific environmental covariates. This gives us the flexibility to represent climate-driven movement patterns or ontogenetic shift in habitat use. This new multi-region framework has been already applied to the northern and southern components of black sea bass, as shown in the recent work by Tim Miller and his colleagues Kirsten Curdy and Alex Hansel. With these advancements in WAM, I was able to develop this spatial MSE framework, which we call SPASAM-MSE. It is implemented as an R package, and it includes a wide range of tools to address different spatial questions and management challenges. The flowchart here provides a snapshot of how SPASAM-MSE incorporates spatial structure throughout almost every part of the MSE process. If you take a close look at the chart, you can see we begin by defining the spatial resolution of the population and fisheries dynamics in the operating model. And then we define the spatial resolution of data collection or processing, or how those data are aggregated. Finally, we determine how the spatial structure of the assessment model should align with the true population structure. In addition, harvest strategies can be also designed to include spatial considerations. We have also created a GitHub webpage for this package, which provides many examples and vignettes for users who want to apply MSE to a wide range of stock assessments or management problems. And I want to emphasize that this platform is not limited to spatial applications. It can be also used for single region MSE as well as for simulation estimation experiments for any age-based assessments. On a related note, we're currently undergoing a major upgrade of this package. The new version will include a set of user-friendly GUIs so that people who are kind of new to the state-space world can more easily condition an operating model on their stock and run an MSE in a relatively short amount of time. We're aiming to launch this updated platform with additional features at the beginning of next year, so please stay tuned. Regarding the functionality of movement modeling, I used the current version of WAM and extended its functionality to incorporate more movement dynamics. This extended version of WAM, which is included in our SPASAM-MSE package, can now model a range of movement patterns, including natal homing, metapopulation structure, and ontogenetic movement. This gives us more flexibility to mimic the complex movement patterns we observe in different species around the world. The platform is built in a modular way, so users can explore and customize many different features. And the package will continue to be improved with contributions from our regional collaborators and active users. If we look at the flowchart on the right, it shows different modules currently available within the MSE loop. These include operating model, observation model, data collection and processing, development and diagnostics of assessment model, methods for calculating reference points, alternative harvest control rules, methods for projecting population dynamics and generating catch-up bias, and the ability to incorporate different types of implementation error. In addition, environmental effects can be included in different parts of the MSE framework to help address climate-ready fisheries questions. We also use ShinyR as a tool to enhance user accessibility. Here is just one of the examples of our ShinyR application. So specifying movement configurations can be tedious and not very user-friendly, honestly, because it often involves working with large, high-dimensional arrays, especially when the movement dynamics are complex. To make this easier, I developed this Shining R app that lets users specify their spatial structure and movement scenarios in a more interactive way. In addition, the platform includes built-in functions that can automatically generate hundreds of figures to help users compare management strategies in a holistic way. And the best part is that no coding is really required for summarizing all these MSE results. We have a manuscript that describes this package in detail and highlights several potential applications, and it is currently under review in the Canadian Journal. The package has already started to receive some attention both regionally and internationally, which has created many opportunities for us to collaborate with different groups of scientists and further expand its functionality. More importantly, users are already applying this platform to a wide range of stock assessment and management challenges across different fisheries. On the right, I've listed some of the ongoing and completed projects that are using this package. These will include evaluating um, climate impacts on fisheries management, developing and diagnosing spatial stock assessment models, testing catch apportionment strategies, exploring biological reference points, addressing emerging data challenges, and even designing surveys in the context of MPAs or offshore wind farms. Now that we have a kind of fully functioning MSE package, we want to use it to address real world challenges in fisheries management. This is one of the applications I want to highlight today, and it's an ongoing research project, and we're currently preparing a manuscript for that. So the central questions we want to ask is if we must continue using a single region assessment model for a stock that likely has some spatial complexity, is single region management actually adequate for managing a spatially structured population? Or, in other words, what can we do to improve the effectiveness of single region management so that we can still achieve sustainable fisheries at the global scale and also regional scale? When we rely on a single region assessment model, we are implicitly ignoring the underlying spatial population structure. This can reduce both population resilience and long term yield. It should be noted that even with a single region model, managers or stock assessment scientists still need to allocate the total allowable catch, or TAC, coming from the assessment model across different regions. And this is what we call catch apportionment. And this is usually done using different empirical methods. Therefore, catch apportionment becomes the key link between a non spatial assessment and a spatially structured population. If apportionment is done incorrectly, it can lead to localized depletion even when the overall stock appears healthy. But if apportionment is done appropriately, it can actually help alleviate some of the negative impacts of ignoring spatial structure in the assessment model. If we look at the literature, previous stochastic projection studies have already looked at empirical catch allocation strategies, but those projections do not really capture the full feedback between assessment, harvest control rules, and population dynamics. This is why a closed loop MSE is very needed, because it will allow us to test catch apportionment strategies in a more dynamic, feedback driven framework and evaluate which ones are robust to uncertainty in both the system and the assessment. We use black sea bass as our study species because it is currently, I think it's the only one assessment model at NEFSC that takes the full advantage of the spatial features in RAM. In the assessment, black sea bass is modeled with two spatial components, a northern component, or region 1, and the southern component, or region 2. The population exhibits strong natal homing behavior. Empirical evidence indicates that natal homing migration occurs in May right before the spawning season in June and July. And after July, fish from the northern population have a probability of moving south and mixing with the southern component or southern population. Then, from January through April, those northern oranging fish in the south will gradually move back to their natal region in the north. Sorry. This complex movement pattern creates increasing challenges for fisheries management. On top of that, the presence of multiple fleets in each region adds another layer of complexity. Specifically, each region has a commercial fleet and a recreational fleet, giving us a total of 4 fleets across the spatial domain. And for each region, the current spatial stock assessment model uses vast integrated survey indices to inform regional population abundance. Therefore, the complex spatial structure and movement dynamics, combined with multi-fleet fishing patterns, make black sea bass as an ideal case study for exploring the effectiveness of different catch apportionment strategies within an MSE framework. To best mimic the black sea bass fishery in the US Northeast, we conditioned our operating model using the input data from the black sea bass stock assessment along with some parameters estimated from the most recent spatial black sea bass stock assessment model. These slides shows the biological and fishery heterogeneity that we incorporated into the operating model. On the left, you can see variations in weight at age, maturity at age, selectivity at age for each fleet and survey, and historical fishing pressure across all fleets. On the right, the table summarizes key parameters governing population and fishery processes in the OM. Overall, these inputs give us a realistic operating model that reflects the biology and fishery of black sea bass. Here, the operating model has 2 spatial regions, but assessment model is a single region stock assessment model where all data are pulled before entering the stock assessment. As a result, none of the spatial dynamics in the operating model are explicitly captured in the assessment model. Then, the assessment provides a single estimate of population status, which is used to generate one total catch recommendation through the harvest control rule. Because the assessment is single region, this total TAC must then be apportioned across regions and fleets before it is fed back into the operating model. These proportions become critical because they can directly affect fishing behavior of commercial and recreational fleets in each region. And the way we define these proportions, like I said, needs to follow some empirical methods. So in the next slide, I will describe what those empirical methods are. Here are just 5 catch apportionment strategies we tested so far. Again, these proportions are critical because they directly shape how commercial and recreational fisheries behave in each region. First is the baseline, which is the equal, or we call it uniform strategy, meaning that TAC is split evenly across 4 fleets, so 25% each. Second, a landing-based strategy, where we first look at the historical total commercial landing and the total recreational landings. We use those to divide TAC between these 2 types of fishery, and then split catch advice for each fishery evenly across its 2 fleets in 2 regions. Third is another landing-based approach, but more direct. We use historical landings from each of the 4 fleets individually to determine their proportions. Fourth is a survey-based strategy. We treat that survey index as a proxy for regional biomass, for example. So TAC is apportioned across regions based on the survey biomass and then split evenly between commercial and recreational fisheries or fleets within each region. And finally, the hybrid strategy, which combines both survey information and historical landings. Survey determines the regional speed, and within each region, landings determine how much goes to commercial versus recreational fisheries. Once the apportioned catch advice is fed back to each fleet in the operating model, the system iterates through the MSE feedback loop across many assessment cycles. At the end of MSE, we can examine how the population responded under each catch apportionment strategy. We can also look at whether the population remains in a healthy state, both globally and regionally. And we can also look at total catch to see whether each strategy maintains a good landing through the feedback period. These become key metrics for evaluating the trade offs among different apportionment strategies. To ensure that our results are more generalizable and not really limited to the specific movement patterns of black sea bass, we extended our simulation to a broader set of operating model scenarios. These scenarios capture a wide range of real-world movement dynamics and spatial complexity, biocomplexity in particular, that can occur in many species around the world. Here you can see examples such as metapopulation structure, relatively high movement rates, unidirectional movement, ontogenetic movement, time-varying movement, and movement in combination with climate-driven recruitment, and also movement in combination with some density-dependent recruitment. By testing our catch apportionment strategies across this full suite of scenarios, we can evaluate how robust these strategies are under different spatial and biological conditions. In total, we included 16 operating model scenarios, and we can finally run our MSE simulations. Again, this is an ongoing research, so all simulations are currently being run on the Stony Brook High Performance Computing Center, and we're now in the process of analyzing some results, and we hope to answer the key questions listed on the right. For example, how robust are each of these catch apportionment strategies? Which ones consistently perform well across different spatial scenarios? And what guidance can we provide for situations where managers or stock assessment scientists must use a single region stock assessment models for populations that are actually spatially structured? All right, now let's move on to the second application. Here we are looking at a different stage of stock assessment, the situations where managers or stock assessment scientists have already added some spatial structure into management. In many fisheries, the population gets split into multiple management units or stocks because there are clear, clear biological or spatial differences. A good example in our region will be Atlantic cod or yellowtail flounder, where multiple stocks have been defined to better support sustainable fisheries and management. But even when we split a population into multiple stocks, in reality, fish can still move across those boundaries. So that raises an important question for us, particularly for people in the state-based world. Can the random effects that we actually put on the process, such as numbers at age transitions, or some people call this random effects, implicitly capture some of that movement? And if they do, does that actually help the assessment and improve management performance? For state-based assessment models, if we look at the population dynamics equation for numbers at age, we can see an error term added to the survival. This is what we call NAA random effects. The idea behind this NAA process error is that it absorbs actual variability in survival, things like irregular mortality, fish moving outside the entire spatial domain, or other type of mortality or loss process that isn't directly tied to natural mortality, fishing mortality, or movement. So in theory, NAA random effects could be picking up movement signals, even if movement is not explicitly modeled. In our paper published last year, we conducted a large simulation estimation experiment, and what we found was that models that included NAA random effects, even when they are incorrectly included, still perform relatively well. That suggests NAA random effects can act as a bit of a catch-all. Based on that work, we actually recommended using NAA random effects as the default starting point in stock assessments for a few of reasons. First, they introduce flexibility because NAA deviations can soak up population and fishery processes that aren't explicitly modeled. Second, they reduce bias. We find that estimates of management quantities were generally less biased. Um, Even when the operating model didn't include NAA random effects. Third, they offer a plausible biological interpretation. These deviations can reflect migration events, unexpected mortality, or other unobserved processes. But here's the gap. We still don't know how much NAA random effects can actually help when the issue is movement. At least it has not been explicitly tested. To answer that question, we designed an MSE simulation where operating model represents a medium-leaf groundfish species with a natal homing behavior. In this system, fish migrate back to their natal region during the summer, and they do not move during the spawning season in the fall. And then movement resumes in spring and winter. We created two movement scenarios with different magnitude of movement rates. But today, I would just focus on the first one, the scenario where movement rates are high. In this scenario, movement is region specific, and there's a higher probability of fish moving from north to south, and a lower probability of movement in the opposite direction. Sorry, I forgot to mention that each region has one fleet and one survey. This work was recently published in the Canadian Journal, and the link is shown here if you want more details. So, when we suspect that fish are moving between regions, we actually have several options. As a stock assessment scientist, we have several options for how we set up our stock assessment model. On the right side of the slide, I'm showing kind of four common ways we can structure the assessment. At the top is the simple panmictic model or one region stock assessment model. We have one population, one aggregate fleet, and one aggregate survey. This is the traditional approach, and it does not explicitly capture movement. A second option is the fleets as areas model, where we still treat the stock as one population, but we keep the fleets and surveys separated by region. This gives us a little more spatial signal, but movement, again, is still not really explicitly modeled. And then a little bit further is the spatially disaggregate model, where we model the population as two separate regional components. Here we have two populations, two fleets, and two surveys. But still, again, still no explicit movement between regions. Finally, we have the spatially explicit model with movement, which is the most realistic for species that truly move across regions. This allows us to estimate movement rates directly and fully account for spatial population structure. These are kind of assessment structures we compare to evaluate how well different approaches handle movement dynamics. For each type of assessment model, we also have the option to include NA random effects or not, just as we proposed. And actually, this choice matters. Our hypothesis was that NA random effects might help implicitly explain some of the movement variability that we don't model directly. So, to make a clean apples to apples comparison, we built pair versions of every type of estimation model or assessment model, one with NOAA random effects and one without NOAA random effects. This pair design lets us evaluate two things: how spatial complexity in the assessment model affects performance, and how much NOAA random effects contribute on top of that. By comparing these models side by side, we can see how the interaction between spatial structure and NOAA random effects influence stock assessment and management outcomes. Let me quickly walk through the MSE setup for this experiment. We start with a 30-year historical period followed by a 30-year feedback period where the assessment and management loop is running. Assessments are conducted every 3 years, giving us a total of 10 assessments over the entire feedback period. We use an F40% harvest control rule for each OM scenario, and we run 100 stochastic realizations to capture uncertainty in biology, observation, and implementation. On the right are some of the key performance metrics we evaluate. Actually, we have more, but this is just a subset of the metrics we highlight today. Short-term and long-term catch, fishing mortality, and spawning stock biomass, probability of overfishing and being overfished, terminal year population status, and average annual catch variation. All of these metrics allow us to kind of examine management performance across all assessment models and NOAA configurations in particular. Here are the long-term performance results. We summarized three key metrics here: relative difference in catch, fishing mortality, and spawning stock biomass. So on the y-axis, what you're looking at is the relative difference between each estimation model and the baseline estimation model. The baseline being the spatially explicit model with movement fixed at the true value. On the x-axis, we have the estimation models arranged from simplest to most complex. To help compare the role of NOAA random effects, we shaded the background. So you can see gray panels show models with NOAA random effects, and white panels show models without NOAA random effects. You will also notice there are three rows of the results. The first two rows show regional performance for region 1 and region 2, and the bottom row shows the global scale performance. Overall, we find a very consistent pattern. Estimation models with NOAA random effects tended to more closely match the baseline estimation model than models without NOAA random effects. You can see these across all of these three metrics like catch, fishing mortality, and spawning stock biomass. And the differences are especially noticeable for global SSB, where EMs without NOAA dramatically diverge from the baseline. We also see that the simple panmictic model or one region model with NOAA random effects actually performed reasonably well at the global scale, but it did show signs of localized overexploitation because it cannot capture regional dynamics. The model that performed the best overall was the spatially disaggregate model with NOAA random effects. It most closely matched the baseline EM and generally outperformed the other EMs. However, even the spatially disaggregate model was not perfect. It still resulted in about a 10% reduction in global SSB over the long term. So, while NOAA helps, it doesn't completely solve the issues created by ignoring spatial structure, in our case. Terminal year population status summarized across 100 realizations. In this plot, the left panel shows models with NOAA random effects, and the right panel shows the models without NOAA random effects. I forgot to mention that we also tested the operating model under three different historical fishing pressures, which is why you can see three rows. But the overall pattern is fairly clear. Without NOAA, which is on the right, terminal year F is almost always above the threshold, meaning that overfishing is likely occurring. If we take a step back and look at holistic performance across all key metrics, the pattern is very clear. On the y-axis, we have different assessment or estimation models, and on the x-axis, we have their normalized performance scores. The shaded rows, again, represent models that include NAA random effects. And across all OM scenarios, those NAA models consistently achieve higher total scores than their counterparts without NAA random effects. This shows that incorporating NAA random effects broadly improves management outcomes, not for just one metric, but across catch, fishing mortality, SSB, risks, and variability. To sum up, here is what we find. Models with NA random effects consistently outperform models without them across catch, F, SSB, and risk metrics. Adding NAA improved overall management performance. But NAA random effects cannot fully replace explicit movement modeling. When movement rates were high, NAA can help, but not enough to fully recapture the underlying spatial dynamics. So we see NAA random effects as an intermediate solution. They are useful when you suspect movement, but cannot model it directly, either due to data limitations or computationally complexity. And because of that, our recommendation is simple. NAA random effects should be the default starting point in state space stock assessments. They add flexibility, reduce bias, and improve robustness, while still acknowledging their limits in highly dynamic systems. With that, I will stop here. I think I will still have some time to for Q&A session. I'll be happy to take any questions if there's any. Thank you.
Thank you so much for your presentation. Audience, this is Cassandra, your host from NOAA Library. We have plenty of time to answer your questions, and we would love to hear them. So, for our first question, thanks for the presentation. What types of information is needed about the stock in order to move the MSE in a spatially explicit direction?
Can you hear me now?
Yes.
Okay, that's actually a good question, and it depends on the data availability. If you have a pretty good geo reference data in terms of biology, for example, you can tell that there's a biological heterogeneity, spatial domain. Um, there's differences between populations, and you also have those data associated with those biology. You may be able to move the one region stock assessment to spatially explicit model without movement estimated. And if you have your tagging or mark recapture module or data in your model, you may be able to have the real spatially explicit model with movement. I hope that answered your question.
Great. Thank you so much. Our next question is, thank you for the great talk. In your first application, how are the fleets treated in the simulated one area assessment? Do you have separate fleets and selectivity for each regional fleet and gear similar to a fleet as areas model?
That's also a good question. Let me read the question again. So, are you talking about the OM or EM? So, in the OM, we do have four fleets, and those four fleets will be associated with different selectivity curve. And in the EM, we combined, for example, we have commercial fleets in each region. We combine the fleets to be the aggregate commercial fleet, and we also have a combined recreational fleet in our EM. So that's for the one region, and you're talking about fleets as areas model. We actually use all of those four fleets, I, I think, to kind of represent the spatial heterogeneity in fleet dynamics.
All right, thank you for your response. Our next question. Great presentation. I was wondering if the framework can deal with sex-specific movement. Also, is the framework set up for researchers to add new modules/options for various biological relationships, for instance?
First, we do not have the ability to model sex-specific movement so far, but it looks like it's a direction for the future that we can try to incorporate those functionalities. Because I know there's a lot of stock assessments use sex-specific design. And the second question is, yes, we do welcome all the researchers or regional collaborators to brainstorm some new module or new design to improve the functionality of our SPASAM-MSE package to be able to answer some of other challenge questions related to fisheries management in the U.S.
Great, thank you. Our next question. Sometimes fishers disagree with how scientists randomly sample species in a space because the fishers know there may not be fish there. They may feel like this skews the surveys. Could state space stock assessments help address this?
Um, it's a very tricky question. I would say I I hope so. I hope the state-based stock assessment can help, um, but I would say it's still a relatively new model, and we need more evidence to demonstrate if this is really helpful or not. But at least one of the beauties of state-based model is it actually help recapture the true population dynamics. I would envision that could be more informative than other traditional statistical catch and age models.
Awesome. Thank you for your response. Our next question, what constraints do you include on the RE for NAA? I worry that unconstrained devs provide too much flexibility that the information about population processes is lost.
I want to answer. Well, Rick, this is a good question. I want to answer that in two ways. First, if we have strong evidence of what natural mortality is, what fisher mortality is, or movement, other process errors, and I think NAA here can serve as an additional feature to explain some unexplained variances or processes underlying the population dynamics. Um, so I do not think it will give too much flexibility to NAA because based on our simulation estimation work before last year, we did find if the truth is natural mortality, for example, is varying over time. If you have a model with natural mortality and NAA both treated as random effects, the model can identify natural mortality as varying. So it will not be a problem that NAA will strongly um, interact or confound it with other major processes. So I think having constrained deviations can be useful if we do find out NA random effects or the magnitude of NA random effects is very high. That must means we probably have some model misspecifications or we probably have some major process on model in your model. So that's something we should think about, and I will think simulation estimation work will help to answer this question.
Great, thank you so much. Our next question we have, thanks for the interesting talk. I was curious how you define your regions and whether there was a difference in survey spatiotemporal extents across years, and if so, how did you address this?
So the regions, in my case, is defined based on the biological and fishery differences between these two regions. And we can clearly see there's some biological characteristics of northern population, which is slightly different than the biological characteristics of the southern component. And also the fisheries, if you look at the fishing pressure, they're kind of different. So that's how we can sort of differentiate two regions and having two regions in our simulation study.
Awesome. Thank you so much. And that was the last question in our queue, which is perfect timing because we are at 3:59. And so I will go ahead and end the Q&A and we can wrap up today's session. Thank you again for joining us today and sharing your work with us. And thank you, Bai, for organizing today's event. Audience, please join us again next month for the next National Stock Assessment Science Seminar. Take care and enjoy the rest of your day.